In today's lesson, we're really coming back to our study of complex numbers. The last few lessons have been about polynomials and the complex roots that they can have. We've sort of taken a break from this deep look at complex numbers. And today we're going to be coming back and really looking at some of the powerful ways that we can use polar form to our advantage. It was something that we kind of just learned before, and then it just sort of sat there. So we're going to do a lot with it today, and we're going to get a really exciting result. So before we get started, let's take a deep breath. And let's begin. So again, it's been a couple days since we've sort of really talked about complex numbers in depth, and so I wanted you to recall that we do have two different ways of representing a complex number. Now, we've got the Cartesian form, where we really think about it in a rectangular fashion. There's a real part of the imaginary number and an imaginary part, and we sort of imagine going over x in the real and up y in the imaginary, and sort of imagining that there's this sort of point that's out here, maybe an arrow that's going up to it, and that's one way of visualizing this complex number. And the other way, though, is via polar form, that if we imagine that indeed there was still a real axis and an imaginary axis, it was still over x and up y, but instead of thinking about rectangularly, we think about the angle that's made with the positive real axis and the sort of the length, the distance from the origin out to that point. We can think about that x plus iy being the same thing as r times cosine theta plus I sine theta. And our shorthand for that was this r cis theta, the cis being the cis being short for cosine, I sine. So now that we've got a brief bit of review out of the way, I'd like to move forward into the sort of exciting result that we're getting in this lesson. So actually, depending on your pattern recognition skills from a previous lesson, I was really sort of trying to lead you guys to seeing this. So you might actually have seen these sort of on your own individually, but now we're really formally learning them. So the first key point, imagine that you have two complex numbers that are given in polar form. So I'm calling the first one z and saying its modulus is r and its argument is a. The second complex number I'm calling w, and its modulus is p and its argument is b. So what this key point says is, when you multiply those two complex numbers together, you can do it by multiplying their moduli together and adding their arguments together. Which means, if we had these things written in rectangular form, we would multiply them together by sort of FOIL, by binomial multiplication. But if they're in polar form, we can do it by sort of using this property of polar numbers. We get a really similar result for division. If I have the same two complex numbers given polar form, when you divide those two complex numbers, you get the result by dividing the moduli, so r divided by p, and then subtracting the arguments, a minus b, to give you the new argument. Now, I've got some examples of this, and then we're going to end up extending it into some other things as we move through this lesson. If you're interested, by the way, you could actually go back to some of those old assignments we did where I was asking, like, hey, do you notice anything about the modulus and the arguments of these products? And you might be able to see that this is something we've actually been looking at for like 2 weeks now. I just hadn't told you that it was happening. I was hoping that some of you would see it on your own. So now we're going to look at a really concrete example. So we start with z being 5 cosine pi plus pi over 3 plus I sine pi over 3. And we've got the complex number w, which is 3 times the cosine of 2 pi over 3 plus I sine of the 2 pi over 3. You're being asked to find the product of z and w and the quotient of z and w. So according to the property that we just learned on the previous page, if we want z times w, all I need to do is multiply together the moduli, so that would be 5 times 3, and then cis, and then I add together the arguments. Pi over 3 plus 2 pi over 3 is, well, it's going to be pi. And so when I work through this is 15 cis pi. Now, it might actually be fun to sort of like confirm this and look at it to make sure that this is the case. So this is the answer I got using this new property, but let's take a moment and sort of convert. What is z in rectangular form? What is w in rectangular form? And what is this in rectangular or Cartesian form? Let's check all of those things and sort of make sure it all matches. So z here would be 5 times the cosine of pi over 3, which is 1/2, plus I times the sine of pi over 3, which is root 3 over 2. So z here is 5/2 plus I times 5 root 3 over 2. And w for us is 3 times the cosine of 2 pi over 3. The cosine of 2 pi over 3 is negative a half, and then plus I times the sine of 2 pi over 3 is root 3 over 2. And so w for us winds up being negative 3 halves plus I times 3 root 3 over 2. So if I multiply these two things together, if I multiply 5 halves plus I 5 root 3 over 2 with negative 3 halves plus I 3 root 3 over 2, I'm going to need a little bit more space here. If I work through and do this, these two things together are going to be negative 15 fourths. These two will be plus 15 root 3 over 4I. This and this is negative I times 15 root 3 over 4. Oh, that's neat. So those drop out. And then I get plus I squared. The 5 times the 3 is 15. The root 3 times root 3 is 3 over 4. The I squared we know is negative 1. Giving ourselves just a little more room here. Negative 15 fourths minus, this is 45, so 45 fourths. That's negative 60 fourths, which is negative 15. So I got negative 15 from that. Now, go back up here and look at what 15 cis pi is. 15 cis pi, this is going to be 15 times cosine pi plus I sine pi. But sine of pi is 0, and the cosine of pi is negative 1. 15 times negative 1 is negative 15. Take a look at how much time and space we saved by using this property of polar numbers. In order to multiply those things previously, I had to convert them into rectangular form, then I had to multiply them together and then combine the like terms and wind up down here at negative 15. By utilizing this property of polar form, I was able to get this answer very, very, very quickly. Right? We did also want to do the quotient of these two things, so I'm going to get us some space here and then we'll go back and look at this with z over w. So z over w is really just going to be just as fast. If you want to compute z over w, what we need to do is we need to do the quotient of the moduli, so 5/3 cis, and then we're supposed to subtract the arguments. So this would be 5/3 cis negative pi over 3. And if you really wanted to expand that out, remember, this just means the cosine of negative pi over 3 plus I times the sine of negative pi over 3. So even if you really needed to have this thing in Cartesian form, it doesn't take that long for us to just go through and convert this. This cosine is a half, and this sine is negative root 3 over 2, so this is I root 3 over 2, and then all you'd have to do is distribute this in. So I think, to make it clear, unless the problem specifies the form it needs to be in, we could have been done with the problem here. If they really wanted it in Cartesian form, we just go a little bit further. So hopefully you've been able to see here that now that we have this key point, we can really use polar form to do a lot of good when we're multiplying and dividing complex numbers that are in polar form. Now, in the spirit of practicing this idea of proof, I did want to give us an opportunity to go through the steps of what would it take to prove this result. If someone had conjectured that when you multiply two complex numbers in polar form, you're going to multiply the moduli and you're going to add the arguments. So what would we generally do first when we're trying to set up a proof? Right, when we're trying to set up a proof, we need to sort of set down some guidelines, like what are we working with, right? We might need to say something like let z equal some complex number. And so we might do it the way that we had before. Z is going to be r, cis, and then I'm going to use the capital letter A instead of theta. I'm going to need a second angle for the other one, and so I just want to use sort of more recognizable letters. And we'll let w be some other complex number. I need to use a different modulus. I'll use p this time. And then I'll use cis b for this thing. And we want to show, it can be really helpful in proofs to write down something like we want to show that zw is rp cis a plus b. So it's almost like you're stating what you're going to use, and then you're also stating where you're trying to get. So it's almost like you're setting up your own show problem. Okay? Now, we need to prove this, so I can't just say, oh, well, yay, we have a property, like I'm trying to prove that thing. So the only other way that I know how to multiply these things is to multiply them in rectangular form. So my thought on this is, all right, well, let's go back then and let's consider z times w. And let's actually write these out as r times, now remember what z is. It's cosine a plus I sine a. That's z. I want to do this times w, which is p times cosine b plus I sine b. All right, now I guess my only thought here is I could try like multiplying these things together and hope for some good news. I mean, now that I look at it, you've sort of got this r times p here. I could pull those to the front, and that feels good. I at least have the r times the p. So I have rp times, and then maybe we FOIL these things together. You'd have cosine a times cosine b, cosine a cosine b, and then we'd also have these ones. So plus I cosine a sine b. All right, I'm going to keep going through colors here. Then I would do this one times this one. That would be I sine a cosine b. I'm almost out of space, but I think I'm going to make it here. And then this one times this one, plus I squared, no, I'm going to run out of space, sine a sine b. Kind of barely fit that in. I've got all of this here. Wow. All right, now what's a tactic that I've used before when I'm working with things like this? Actually, I suppose even before I get to that, simplifying here. This I squared, we know this is going to be a -1, right? So this is really sort of like a subtraction that's happening here in red. So another strategy that we've used is we've used the idea of bringing the real and the imaginary parts together. So what I'm going to do here is I'm going to pull the real parts together in the front and write them in black, and I'll put the imaginary parts on the right in blue. So we still have the RP on the outside of this whole thing, and then the real parts are these ones. Cosine A cosine B minus sine A sine B. This is all the real part. And then plus I times, I said I was going to do this in blue, right? So I times cosine A sine B, that's from there, and then this one here, plus sine A cosine B. Do these look familiar at all? Like, does this look like anything that we've ever at any point seen before? They do, actually. I don't know if you recognize them. These are the compound angle formulas. This guy right here, this is cosine of A plus B. And this guy over here in blue, this is the sine of A plus B. You may remember in these compound angle formulas that the cosine one had the opposite sign inside, and the sine one had the matching sign inside. And I still have this RP back at the beginning. Oh, wait, would you look at that? What I have here is I have RP cosine I sine. The arguments are the same. This is RP cis A plus B, which is literally what we set out to show in doing this. And so we write that as our concluding statement. And just like that, we've proven this result that we started with. You can go through a very similar process to show the same property for division. I'm not going to go through it for length purposes, but it's definitely something that you could do. It's something that you guys are capable of doing. So you might have thought of it yourself, but you might not have noticed this. It turns out this property of polar form actually makes it really useful when we're working with powers of complex numbers. Imagine that I asked you to do 1 minus I to the 10th power. No one wants to take something and raise it to the 10th power. Like, you could do it. You could binomial multiply this thing again and again and again and again and again and again. You could do that, but it would be really frustrating. What if instead I imagined taking this as 1 minus I times 1 minus I times 1 minus I and multiplying them, but then going, multiplication works better in polar. Let's take this thing and put it into polar form. If I have if I have 1 minus I and I want to convert this into polar, all I'm going to need to do is I'm going to need to find what the modulus of 1 minus I is and what the argument of 1 minus I is. Remember, the way that we've done this before is by thinking about the argand diagram. 1 minus I is down here. And actually, I think we can sort of see that this is a unit circle value, right? The magnitude of this thing is going to be the square root of 1 squared plus negative 1 squared. That's the square root of 2. The argument would technically be the inverse tangent of negative 1 over 1, but I think we can all see here that this is a 45-degree angle. This is just negative pi over 4. So this thing is really saying the square root of 2 cis negative pi over 4, and I'm imagining multiplying this thing by itself 10 times. Well, if I multiplied this thing by itself 10 times, wouldn't that just mean I would multiply this thing by itself 10 times? But we have a notation for that. That's literally just this to the 10th power. And if I was going to multiply this thing by itself 10 times, what would I do with this argument 10 times? Wouldn't I add it to itself 10 times? But adding something to itself 10 times, we have a notation for that. That means 10 times the thing that you wanted to add to itself 10 times, right? Now I just need to sort of clean this thing up. The square root of 2 to the 10th power, that's like 2 to the 5th power. And then this is cis, I could reduce this down to 5 and 2, so negative 5 pi over 2. This is 32 cis negative 5 pi over 2. But negative 5 pi over 2, that's like negative 2.5 pi. So that's like going backward around the unit circle one time and then going another negative pi over 2. This is the same as 32 cis negative pi over 2. And then we can even sort of convert this further. 32 cosine negative pi over 2 plus I sine negative pi over 2. Well, the cosine of negative pi over 2 is 0. The sine of negative pi over 2 is negative 1. And so our answer here is negative 32i. So, I mean, believe it or not, we were able to figure out that I minus 1 to the 10th power is negative 32i. And it took us about 3 minutes, and we did it by hand. Like, this is a really, really powerful tool in specific instances. In fact, that thing that I just went over is so commonly used that it's got a name. There's this thing, it looks like a Demois. This is pronounced Demois Theorem. So Demois Theorem literally says, if you take a complex number that's written in polar form and raise it to a power, you can accomplish that by raising the modulus to a power and multiplying the arguments by that power. So we really just sort of made sense in the previous example of sort of why it would make sense to do that, but I want to let you know now that thing is called a Demois Theorem. It's absolutely a thing that you're expected to know and be able to use to your advantage. And I'm going to go through an example or two here now where you'll get a chance to use that and to see how powerful a tool this can be. All right, so talk about a horrible looking problem. The square root of 3 plus I to the 8th power divided by negative 1 minus I squared. We could do this in rectangular form, but it would be a mess. So I want us to use Demois Theorem. So start the problem by sort of working out. If you feel good, do it on your own. If you need some hints and some guidance, here's what I'm going to tell you. Your process here should be powers are going to be easier to deal with in polar form. So convert the top number and the bottom numbers to polar. Then use Demois Theorem to apply the powers. And then remember that you can divide complex numbers by using the property that we learned earlier. So I'm going to go ahead and go through that now. So the square root of 3 plus I need to find the modulus, and I need to find the argument. Doing that is easiest when I look at it in an Argand diagram. Root 3 is longer, and I1 is shorter, so we're looking at something like that. The modulus of this is the square root of 3, that's the square root of 3 squared, plus 1 squared. So that's 2. Okay, that's a really nice modulus to work with. The argument for us is going to be inverse tangent of 1 over root 3. I recognize that as a unit circle value, and as I look at this more carefully, I recognize this is pi over 6. And I sort of check it against, like, yep, it makes sense. This is first quadrant. Pi over 6 makes sense. Great. So this thing here is 2 cis pi over 6, and I'm being asked to raise that to the 8th power. Demois Theorem lets me take this and make it 2 to the 8th cis, and then I'm supposed to multiply this to here. So this is going to be 8 pi over 6. So we've already simplified the numerator. Now, I could multiply this thing out, I could expand this thing, but I know that I'm going to want to deal with this in like using the properties of polar form. So I'm going to leave it in polar form. Let's just leave it there and see how much is going to cancel down the line. So now I'm going to go over to blue and work on the denominator for this thing. I'm supposed to work with -1 minus I. Same thing. I need a modulus and I need an argument. So I step over to the argand diagram. -1 minus I is down here. Okay, my modulus is the square root of 1 squared plus, -1 squared plus -1 squared. This is the square root of 2. It's not quite as nice a modulus, but it feels kind of similar to 2, so I'm not mad about it. The argument is going to be inverse tangent of imaginary over real, -1 over -1. That's the inverse tangent of 1, which you might recognize as pi over 4, but we don't want that one. We want the one that's pi more than that, so this is 5 pi over 4. Okay, you might have seen it as -3 pi over 4. Turns out either one of those is going to be okay. So our argument, I'm going to go with 5 pi over 4. So we've taken this now, and we've written this as root 2 cis 5 pi over 4. I now need to take that, and the problem says square it. So using Demois Theorem, this is root 2 squared cis, multiply this thing in, 10 pi over 4. So now I have my numerator, and I have my denominator, and so I'm going to pull those things together and use my properties of polar form division to work through the rest of this. I'll have 2 to the 8th cis 8 pi, I guess I can reduce that, right? 8 pi over 6 is 4 pi over 3. This divided by, I'm going to go ahead and multiply this one out because I feel like it's going to work nicer with this. So I'm just going to call this 2 cis, and I'll reduce this also. This is 5 pi over 2. At this point, I'm now going to utilize my property of complex numbers, or of polar form numbers, that says that when I divide two complex numbers, I can accomplish this by dividing the moduli, 2 to the 8th over 2, cis, and then subtracting the arguments, 4 pi over 3 minus 5 pi over 2. This number in the front simplifies down to 2 to the 7th. For this, I'm going to need a common denominator. Looks like I'm going to go back up to sixths. So this will be 8 pi over 6 minus 15 pi over 6. When I do the subtraction, 2 to the 7th is 128. Cis -7 pi over 6. And I could be done here. If the problem asked for it to be in a plus bi form, all I would need to do is expand this. I would do 128 cosine -7 pi over 6 plus I sine -7 pi over 6. And so I'll run through that for you real quick. The cosine 7 pi over 6, that's all the way over there. So cosine of that is going to be -√3 over 2. The sine of this is -1/2, so minus I times 1/2. Distributing the 128, I get -64√3 minus 64I. And again, sort of like, wow, we were able to work through this problem by hand in about 5 minutes. Again, Demois Theorem, all of these things, incredibly powerful for working with powers of complex numbers. The final thing I'm going to share in this lesson is just a quick note on a geometric interpretation of multiplying by complex numbers. And so I think the thought here is that if multiplying complex numbers causes us to multiply their moduli and add their arguments, then multiplying by a complex number can basically represent a rotation of the first complex number by the argument of the second one. So what I mean by that is if you imagine that you sort of start with one complex number that's right here. Let's say that this is z right here. If I wanted to sort of like rotate this thing by, let's say, 180 degrees, I could multiply this thing by a complex number whose argument was 180 degrees and whose modulus was only 1, and it would take this thing, multiply its modulus by 1, so keep it the same length, but add 180 degrees to its argument. So I have one quick example of this here. So imagine that we started with the complex number 5 minus 4i, And I asked you to find the complex number w, which was a plus bi, which results from rotating z clockwise by 60 degrees. So clockwise by 60 degrees. So that would mean that I would want to take my complex number, 5 minus 4i, and if I wanted to rotate it clockwise by 60 degrees, 60 degrees, I mean, since I'm going this direction, that's effectively negative 60 degrees, and I want to do this in radians, so I'd want to use negative pi over 3. So the idea is, if I took this complex number and multiplied it by cis negative pi over 3, leaving the modulus as 1 means I'm not going to lengthen this complex number at all, but multiplying it by something with a cis of negative pi over 3 is going to cause the argument of this thing to get pulled this way by 60 degrees, by negative pi over 3 radians. Now, since the problem wanted this in terms of a plus bi, I'm not going to convert this into polar. I might as well just make this thing rectangular. So I still have 5 minus 4i. The cis of this will be the cosine of negative pi over 3. Cosine of negative pi over 3 is a half. And then the sine of negative pi over 3 is root 3 over 2. And we have our I because this is cis. And now I just need to multiply these. 5 times a half is 5 halves. 5 times this one is minus I, 5 root 3 over 2. This one here is minus 2i. And here I have plus I squared, 4 root 3 over 2. So it's a little bit messy, but I mean, we can work through this. It's nothing we're incapable of doing. This is going to be negative 1. So I'm going to have 5 halves minus 4 root 3 over 2. And then it looks like I've got minus I. And inside of this, I had 5 root 3 over 2 minus 2. So this is certainly not a pretty answer, but this complex number right here is indeed this thing that has been rotated by 60 degrees in the clockwise direction. There aren't a ton of questions that really heavily utilize this as a separate thing, but the idea of rotation by multiplication is definitely something we're going to get into on our next lesson. But let's practice the basics that we have now. We'll get to that when we get to it. I hope that this all made sense. If you've got questions, let me know. And as always, best of luck in working through the problems.